Don't forget to subscribe and ring that bell.
This is it. AP Calculus, AB 2019, final question, free response question number 6. No calculator. Puh. Keep it. Keep it in the back pocket. We don't need it. We're going to use our brain, our knowledge, and we are going to knock this out of the park. Let's go. Question number 6. Functions. F, G, and H are twice differentiable functions with G of 2 equaling H of 2, which is 4. The line y equals 4 plus 2/3 x minus 2 is tangent to both the graph of G at x equals 2 and the graph of H at x equals 2. Find H prime a 2. When I first read this problem, I thought it was maybe a joke because it's asking us for the derivative of H. The derivative of H is like saying the slope of H at x equals 2. And this line right here is the line tangent to H at 2, which means this line touches H at 2 and has the same slope. This is the slope right here. It's 2/3. The slope is 2/3. So I don't know. I guess that I'm just gonna say it's 2/3. Okay, and it's the same as the slope of the tangent line at x equals 2. I mean, it's just that simple. Don't overcomplicate it. All right. B says, let a be the function given by a of x equals 3x cubed hx. Write an expression for a prime of x, then find a prime of 2. All right, let's start first things first, a prime of x. If this is a, let's find the derivative of a first. Product rule first, which is 3x cubed times the derivative of the second. The derivative of h is just h prime of x plus the second, just as it is, h of x times the derivative of the first, which is 9x squared. All right? 9x squared is the derivative of 3x cubed. Okay, this is the expression for a prime of x. We've already answered the first part. Now we need to find a prime at 2. I'm literally just going to throw a 2 in for all these x's. All right, let's go. 3 times 2 cubed times h prime of 2 plus h of 2 times 9 times 2 squared. All right, well, this is 8 times 3, 24, times, we'll leave h prime of 2 alone for a second. We'll leave h of 2 alone for a second. 2 squared is 4 times 9, 36. All right, let's start with h of 2. H of 2 is the same thing as g of 2. It's the number 4. So plus 4 times 36 is 144. H prime of 2. That sounds familiar. Oh, wait. It was that easy first problem. That's 2/3. We already did that. All right, 24 times 2/3. 3 goes into 24, I don't know, 8 times? 8 times 2 is 16. 16 plus 144. Let's just call that an easy, cool 160. And A is done, and now B is done. Two good, simple problems. 6C. The function h satisfies h of x equals x squared minus 4 over 1 minus f of x cubed for values where h cannot equal 2. It is known that the limit as x approaches 2 of h of x, which is this thing here, the limit as x approaches 2 of this thing can be evaluated using L'Hopital's rule. I love L'Hopital's rule. I love saying L'Hopital. I mean, that's just crazy. Use the limit as x approaches 2 of h of x to find f of 2 and to find f prime of 2 and show the work that leads to your answers. Well, if you don't know what L'Hopital's rule is, okay, if you don't know what L'Hopital's rule is, it's the following, okay? It's the following. When I take the limit of something, if I take the limit of anything, let's just say 2, because that's the thing we have. Of any fraction, we have a numerator over the denominator. And I try plugging a 2 in, and I end up with 0 over 0. I can take the derivative of the top, and I can take the derivative of the bottom separately. Not do the quotient rule here, but take the derivative of the top and the derivative of the bottom separately and leave them in the top and bottom, and then try and plug 2 in again until I get an answer. So if it tells me that I can take the limit as x approaches 2 of h of x, which is x squared minus 4 over 1 minus f of x cubed, and I can end up with a 0 over 0, because that's what L'Hopital's rule does. It's known that that will happen if I try and plug in a 2. Well, I can easily find f of x right now, highlighter, because this bottom has to yield a 0. It has to yield a 0, which means here 1 minus f of x cubed has to be 0. That means f of x cubed has to be 1, right? First of all, I can add f of x cubed to both sides and get this. F of x cubed equals 1. But in my mind, the way it works is the only thing that's going to be 0 is if I take 1 minus 1. So f of x cubed has to equal 1. And there tells me the only way this will work is if f of x equals 1. If I make this a 1, 1 cubed gives me 1. Let's put 1 in for the f of x right here. 1 minus 1, oops, 1 minus 1, because this is what f of x is. We're saying f of x is 1 cubed. That gives us our 0. It works. So f of x has to be 1. And keep in mind, that's when I'm plugging a 2 in there, right? I plug a 2 in there. So that's basically like saying f of 2 is 1. Because we're using L'Hopital's rule when I plug a 2 in for this x. So I'll be plugging a 2 in for this x. So f of 2 is 1. Okay, there you go. We found what f of 2 is. Check. All right. Now, let's find the next thing out. Okay. And we kind of got to use like common sense the way we did here. So let me just back all this up, back this thing up. Boom, 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 boom. Okay, let's get rid of all of this. Delete it. We just said, let's back up for a second here. We just said if we plug a 2 in for these x's, we should get 0 over 0. And that means that f of 2 has to be 1 in this case. Okay, so that's one of our answers right there. But since we get 0 out of 0, what L'Hopital's rule tells me is the following. If I get 0 out of 0, and I know I will because they say in the problem that it's known that I can use L'Hopital's rule, I can take the derivative of the top separately. That's just going to be 2x. Put that over the derivative of the bottom. The derivative of my 1 is 0 minus, okay, this is going to be, right here is going to be the chain rule. The 3 is going to come down. F of x will stay the same on the inside. I shrink my exponent by 1 times the derivative of the inside, which is f prime of x. Okay? This is what we now have. All right? Now I can try throwing a 2 back in to solve it. That's what L'Hopital's rule does. If I end up with 0 over 0, I can take the derivative of the top separately, the derivative of the bottom, and try plugging my number back in. But here's the thing. I know when I plug in a 2, I will get the following. 2 times an x, which is 2 on the top, over negative 3 times f of 2 squared. Okay, because we put a 2 in here, like we put a 2 in here, put a 2 in here, put a 2 in here, times f prime, and here's where our last x is. It's going to be 2. But what does it equal? All right, well, let's simplify it even more. The top is 4. Okay, the bottom. I know f of 2 equals 1. Didn't we just solve that? So this f of 2 is going to be 1. Negative 3 times 1 squared is negative 3 times f prime of 2. The problem is I don't know what f prime of 2 is. That's the second thing I need to solve. Okay, we need to solve f of 2, which we did, and we also need to solve f prime of 2. Here's the catch, kids. G of 2 is 4, isn't it? That's given to us. But what else is given to us is h of 2 is 4. There's a coordinate. When x is 2, y is 4 for my function h. That's a point. It exists. If I take the limit of h as I approach 2, it should equal 4. Okay? It should equal 4. So my limits should equal 4. Now I can easily solve for what I have here. And I put a lot of side notes in and everything, and I apologize, but there's a lot of just like common sense and kind of like really think about it, and it makes sense, and you can go from there. So let's do this. Okay, here we go. In order for me to solve this right here, okay, we'll put this over 1, and we'll cross multiply. Okay, 4 times my 1 is 4 equals 4 times negative 3, which is negative 12, f prime of 2. Just divide both sides by negative 12, and f prime of 2 is going to equal 4 over negative 12, which we will reduce to negative 1/3. Goodness gracious, great balls of fire. And we already figured out that f of 2 was 1. Okay? We used L'Hopital's rule. I'm going to go over this again because there's a lot of writing. We use L'Hopital's rule to figure out that if I put a 2 into my limit, it should be 0 over 0, which means this denominator should equal 0. And when we did that, we came up with f of 2 is 1. It has to be 1. Okay? Then we said, if we're using L'Hopital's rule, let's take the derivative of the top and the derivative of the bottom separately and try plugging a 2 in again, which we did right here. And oh, by the way, because there's a point there, my limit of h as it approaches 2 should equal 4. That's why we set it equal to 4. We did our cross multiplying and came up with our answers. That was a lot. There was a lot of mental, processing. The algebra wasn't difficult. It was using your brain that was difficult. All right. I am going to go out on a limb with 6D here and say that there's something that you can use that I've never seen used before on a calculus test, unless it was from like a 1971 exam that I haven't done yet. But I've done a lot of exams. And we can get away without using this one thing. Okay, but let's just go ahead and do this problem, and I will mention it at the end. All right. 6D says, it is known that g of x is less than or equal to h of x, in between, where x is in between 1 and 3. Let k be a function satisfying that k of x is in between g of x and h of x inclusively for the values of x between 1 and 3. Is k continuous at x equals 2? Justify your answer. All right? Well, first of all, it tells us that g and h are twice differentiable. If they are differentiable, they are also continuous, right? They're differentiable, and therefore they got to be continuous. Okay? We also know that g of x is less than or equal to h of x. G of x and h of x are the same when x equals 2. They're both 4. But other than that, h of x is always bigger than g of x. So if I were to have a graph here, here's where x equals 2. We'll do g of x in red and h of x in blue, all right? At 2, they're the same thing. This is 4. So maybe g of x does something like this, or it comes through here, it goes like that. Maybe h of x does something like this, comes down, hits it. So, whatever. I think you get the point. H of x is always higher from 1 to 3. It's always the bigger function. They're saying that k of x, okay, k of x, which we'll do in a nice gray, is in between both of these. So k of x is something, I don't know, blah, 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 blah. This is k, this is g, and this is h. All right? Now, okay, k of x has to be less than or equal to g of x and h of x. Okay? And at this point, at 2, there is only one value for this. It's 4. And there is only one value for h of x. It's 4, right? If I put a 2 in here, 2, 2, and 2, I know these things. So guess what k of x is? It has to be 4. There's a point there. If there's a point there, it has to be continuous. Okay? So what I'm going to write without knowing, when I started this video, I said there's this kind of theorem, this concept that I never have used on a test. And I can answer this question without using it as such. I'm going to say that since h of x and g of x are differentiable and continuous, and h of 2, I should say, and h of 2 equals g of 2, which is 4. And I'm just writing down what I told you. And k of x, okay, falls in between these two, inclusive. Okay, k of 2 should equal 4, and should be, or is, I should write the word is, and is continuous at x equals 2. Okay? Because h and g converge and almost make one like mini line at x equals 2. And k has to, just because this, k has to make that same line. Okay? That kind of makes sense when you think about it. If h comes through here, boop, and comes through here, boop, and g does the same thing, watch me, comes through here and here, and they form this mutual little line at 2, then that means k has to also make that same line right there. It has to. That's how you answer it without knowing that one oddball theorem that I hardly talk about. Maybe in college classes or other teachers they talk about it. This is something called the squeeze theorem. First of all, I don't know why it's a thicker one. Let's get this thicker writing off. We'll go thinner, thinner. We'll go something called the squeeze theorem. And what that says is, you see H and G as they get closer and closer and closer, they're being squeezed together. And this, it eventually forms that one little line. And it says that they should kind of coexist and be continuous and be the same and be differentiable, all because it gets squeezed so mashed together that it's like just assumed, I guess, basically in layman's terms. I know that's not an appropriate explanation for it, but I'm trying to give you a visual, kind of like the cosmos and black holes and singularity. But you can use the squeeze theorem as your reasoning behind why you would say that k is continuous at 2, or you can use something along that line. Okay, but that's something called the squeeze theorem. If you want to look up in it, you can. I have never seen an answer key besides this one even mention the squeeze theorem, and I've done a lot of these tests. Okay, so I wouldn't freak out about thinking the squeeze theorem is going to be on your final. Maybe if you're in college and you're not taking the AP exam in high school, maybe your college teacher happens to love the squeeze theorem and he wants to throw it on there, then by all means. But if you are taking the AP Calculus AB exam, I would wager that you will not see any reference to the squeeze theorem on there. And if you do, hey, it's 1 in a million. All right? Take it easy and good luck.
Don't forget to subscribe and ring that bell.